So this is our final target in Unit 8, these rational functions. And so we're going to graph them. And the key thing to recall, to realize or recognize with a rational function is what makes it that. Well, the word rational basically means a fraction. But specifically, we've got a fraction where the variable is in the denominator. Okay, so just because there's a fraction doesn't make it rational. It's specifically that you're dividing by x or x squared or whatever. All right, so I've got 3 examples here. I'm looking at the first one on the left. What do you think? Would that be considered a rational function? Do we have x in the denominator somewhere? Are we dividing by the variable? We do. So yes, this is definitely a rational function there on the left. How about in the middle? Would that be considered a rational function? Yes, because there's fractions in it, right? Where are the x's though? Are we dividing by any x's anywhere in this middle one? They're multiplying, all right? So that's the important distinction I want you to recognize, is just because there's a fraction in the equation or the expression doesn't mean that it's rational. Okay, so that 1/2 or 3/8 or 2/5, that doesn't make it rational. It would have to be something like 1 over x or 1 over 2x. That x would have to be in the denominator. Technically, it's not. All these x's are over 1. They're in the numerator. So this one here is not a rational function. It's actually a quadratic function, right? There's that just ax squared plus bx plus c. If we graph that, it would just be a parabola. What about this last one? Just 9 over 33x squared. What do you think? Are we dividing by x? We are, right? There's an x in the denominator. The variable's in the denominator. So guess what? This is a rational function. Hey, one last thing. What about that? Is that a rational function?
Yes, it is. You're dividing by x.
You're dividing by x. Is that all you need?
Yes. Yes.
Based on my definition earlier, that is all you need. This is the parent function for a rational equation. Just like x squared is the parent function for a parabola. It's the most basic, normal, original one that you can have. And if we were to graph this, 1 over x, it's a pretty strange graph. You actually get something like, whoop, whoop, like that. It's nuts. It's these 2 different curves. And the extra strange thing about this graph is that it's not going to touch this line right here at all. Have we ever seen something like that before, where there's a line somewhere on the graph, this invisible line? Yes. Exponential equations or functions. Do you remember how we had something called, starts with the letter A? An asymptote. Yeah, that's considered an asymptote, which is this invisible line that our graph gets really, really close to, but it never actually reaches, it never actually touches that point. And yes, it is on the next slide, everybody. I believe you. Now, why do you think this is? Why do we have to have 2 different halves of a graph? Why can't it be connected? Every other graph we've ever looked at in our mathematical lives is a continuous line from left to right. Why is there this break in the middle? This vertical asymptote, what's the x value right on that line? It's 0. That was fantastic. Yes, that's right. You can't divide by 0. So we can't have a graph that's actually like defined or that exists at that point. You know, if my graph went like that, well, then right here you'd say, oh, but what about when it's at 0 right there? And you're like, oh, no, that can't happen. It doesn't work. So because of this x being in the denominator, there's a specific value that would make it 0 in the denominator that you can't have, right? It's like an illegal move. Can't divide by 0. So that's what gives us this weird graph right here. Here's just a different variation of it. Obviously, like all of our functions, we can move it around on the coordinate plane, move it up, shift it up, down. I can flip it. I can stretch it. all that fancy stuff. And so what you may not have realized is there also was this horizontal asymptote on that previous slide. And so this vertical and this horizontal asymptote, remember that these aren't actual parts of the graph. Only the solid black lines there, that's the actual graph itself. These dashed lines are more like barriers or guidelines to show us where we would draw in the curves of our actual function. This weird shape with these two different groupings like this, it actually has a special name. Just like the U-shaped graph is called a parabola that has its own special name. This is called a hyperbola. Yes. This shape of these two like opposite curves, it's called a hyperbola. Now we're not going to look too deeply into hyperbolas. I'm not going to actually ever talk about why it's called a hyperbola or what it comes from or anything like that anymore this year, so you don't really need to retain that information. I'm not going to test you on what it's called. A hyperbola? In English classes, there's a part of the English language called a hyperbole. That sounds familiar, and students often confuse those two, or at least it's ringing some bells. But this is a hyperbola. It's a name of this graph. It's a type of a conic section, which you get to learn about next year in pre-calculus. Yes. Oh. You get to learn this next year in transitional math at a much slower pace. All right, so that's the graph. What I want us to do today, we're not going to actually be graphing anything today. That's going to be saved for Tuesday. What I want us to do, though, is identify all the different like features or properties of the graph, like from the equation, like where are those asymptotes, right? Because those are important for the graph. If I know where those asymptotes are, then it's pretty easy to draw in the two curves. Just swoop, swoop. And so we're going to find those. And also we want to find a few points on our graph, to identify it. So we're going to try to find like some x-intercepts, some y-intercepts, which we've done that before for pretty much every graph, finding the intercepts. And then once you find all these different parts of the hyperbola, then we'd go ahead and graph it. But again, we're going to save that for next week. Today, I just want to go through each of the 5 different parts or properties of a hyperbola that we're going to identify from the function. And you're going to practice those over the weekend. And then come Tuesday, we'll then put it all together and throw those things on the graph. So here we go. First off, we're going to start talking about these horizontal asymptotes. Remember, horizontal means left and right. I always keep that straight by thinking of the horizon. If you look out over Lake Michigan and wherever the sky meets the sea, Moana style, there's this long horizontal line running left to right. That's the horizon, meaning that direction left to right is horizontal. Are you going to start singing right now?
Think about it.
Okay. I'll allow it. If it's Disney, you're allowed to sing in my class. Yeah, we're good. All right, so these horizontal asymptotes, how do you identify the horizontal asymptote from the function itself? And the way that we're going to determine where this horizontal asymptote is located is by just looking at something called the degree of the polynomial up top and on the bottom. Now that's another term that I haven't used too often, but I have used it earlier this year. Does anyone remember what the degree of a polynomial means? Oh, so degrees, like an angle in geometry, it's actually got a completely different definition than that. So it's nothing to do with like rotation or whatever. Or temperature. It has nothing to do with temperature either. Like how cold is this? It has something to do with the exponents. No, not slope. Third degree. Essentially, the degree of a polynomial, it's a very easy concept. It's just the biggest exponent in a polynomial. And so, like in a quadratic equation, the degree is 2 because the biggest exponent on your variables is a 2. And so all we need to do to determine the horizontal asymptote is look at the degree. And we're going to compare the degree of the numerator. Remember, this is a rational function, meaning there's a numerator and a denominator. So you look at the degree of the numerator, and you compare it to the degree of the denominator. And well, there's only one of three possibilities that could happen. Either the number up top is bigger, the number up top is smaller, or the two numbers are the same. And based on each of those three different possibilities, that will tell you where this horizontal asymptote actually lies. So first off, if the degree of the numerator is smaller than the degree of the denominator, so for example, if you had an equation like, let me slide this over. If you had an x squared over x to the fifth, all right, so the degree is the biggest exponent up top and on the bottom. Even if there were multiple terms, you'd say, all right, the degree of the numerator is 2, and the degree of the denominator is 5. So that would be this situation right here. The degree of the numerator is less than the degree of the denominator. Therefore, we're going to have a horizontal asymptote at the line where y is equal to 0. And hey, on the coordinate plane, what do you call that line where y is 0? It's actually the what? It'd be the x-axis, because it's horizontal, left and right. That's like the x direction. So yeah, if you've got a smaller exponent up top, then you know that your x-axis is going to be your horizontal asymptote. So just draw a dashed line right along that x-axis, and that's going to be one of your asymptotes. All right, well, what about the reverse of that? What if the degree of the numerator is bigger? What if you've got more x's in the numerator than down in the denominator? Well, in that situation, so that'd be something like x to the third over x squared. Yeah. If you've got a larger degree in the numerator, then there's not going to be a horizontal asymptote. All right, now we're not going to actually graph any like this, but in your assignment tonight on Delta Math, there are going to be some where it just says, hey, identify the horizontal asymptote. And if you get this situation, bigger exponent on top, you just select from a drop-down menu, no horizontal asymptotes. That's why I just want to show you what would happen here. It's a good question. What if they're equal? So we then just need to make a little fraction. So when the degrees are the same, then we will have a horizontal asymptote, but it's not going to be at 0. Instead, we look at the leading coefficient. That's just the number in front of both the numerator and the denominator. And you just make a fraction out of that. So for example, if we had a 10x cubed plus x minus 5 over 5x cubed plus 2x squared, something like this. Again, you don't care about all the terms at the end. I just care about the degrees, the first term in each of those. And look at the degree of the numerator and the degree of the denominator. Are they the same in this situation? Right? X to the third, x to the third. So the degree is the same. So we will have a horizontal asymptote at the line y equals. But now to determine this actual number, you just look at the leading coefficients. Those are the numbers in front of the x's. What's it going to be? So it's 10 over 5. And yeah, just simplify it if you can. So that's at y equals 2. So like on the coordinate plane, you'd go to 2 on the x-axis, or the y-axis, excuse me, and you draw this horizontal line. So it's like raised up 2 units. Okay? Those are the 3 different possibilities that you're going to see. Questions on that? It's not crazy difficult. You just need to practice a few of these so you understand what it is with each of those 3 different options. All right, go ahead and try these 2 on your own. When she gets back. So all you're doing is looking at this at each of these functions and just identifying, hey, where's that horizontal asymptote? Right? Y equals what? So this first one, what's the degree of the numerator? That's 2x to the first, isn't it? Like if there is no exponent, you put a 1 there. The degree of the denominator is a 2. So where's this going to be? At 0. Yeah, whenever the degree is smaller up top, that asymptote's at y equals 0, the x-axis. Over on the right, look at these degrees. It's a 3 and a 3. So where's our horizontal asymptote? Will it be at 0? So you make a little fraction with those leading coefficients. Leading just means the one in the front, right? Because there's several coefficients, but we just want the leading, the one at the front with the biggest exponent, that coefficient. And we see 12 over 4, and that can divide to just y equals 3. We okay with this? Is this super difficult to calculate, everybody? Nope. It's basic. You just have to do a few of them to just keep in your brain, oh, what is it when the degrees are equal? Or what is it when the degree is smaller up top? Right? Very basic concept, though. All right, vertical asymptotes. The word vertical means up and down. I often think about basketball players. They jump up a lot, and they always talk about what's your vertical? How high can you go? So I'm thinking up and down, right? They're jumping vertically, up and down. So your vertical asymptotes run up and down, and they're simply the values of x. That would make the denominator a 0. Earlier, when I showed you the graph for the first time, you came up with the fact that, hey, why is there no value at 0? You know, when x is 0, and a couple of you figured out, well, that's because you can't divide by 0 for that basic parent function. Well, same idea here. I'm just going to look at the denominator, and I know that I can't divide by 0, so I have to figure out, well, what numbers that if I plug them in for x there, and then did that calculation, would give me a 0 in the denominator. So I'm not going to have a vertical asymptote where x equals 0, because that'd give me a -6 in this example, you know, and that's fine. We have to think about, well, what are the values that I could plug in for x? Now, just looking at it like this, it's hard to tell. You know, you can guess and check, but there's a better way. What do you think we should do to this function to break it down, to see its individual components a little bit easier? Let's factor, yeah. Anytime you see one of these, go ahead and just factor it all out. I'm going to factor the numerator too, just for fun. -2x, leave me with an x minus 2. And in the denominator, we've got an x minus 3 and an x plus 2. Do you all get the same thing when you factored it? Just want to try to mess up. I guess I could photo math it and double check. No, don't do that. All right, does anything cancel out at all here? Same thing on top and bottom? No, they're all different. So all I want to do to see if there's, or where there is a vertical asymptote is just look at this denominator here. And you probably could tell just by looking at this. What are the two numbers for x that would make that denominator a 0? Yeah, wouldn't you just flip the signs? Isn't that something that we often do in this class when you're solving, you know, by factoring? You get the factors and you just flip the sign. So it's like, well, look at this first factor. What number minus 3 would equal a 0? Well, that would be a positive 3. If I plugged in a 3 for x, I'd get 3 minus 3, which is 0, and that whole denominator would be a 0, and that's where we get into some trouble. But that's not the only number for x that would give us a 0. Look at this second factor that says x plus 2. And so I know that if x were to equal a -2, I'd also get a 0 in the denominator, which we don't want. Therefore, we know we're going to have a vertical asymptote at that point. Questions on this? Go ahead and try that next example on your own then. I know yours is a little bit different, but the denominator is the same, I believe. I just changed mine just so you know that your numerator can't factor. I don't want you to waste time doing that. You should get 2 vertical asymptotes again for this one. 2 different numbers that if you plug them in for x, you'd get a 0 in the denominator. Exactly right. Yeah, 2 times what equals 0? Another 0. Excellent work.
Is that right?
It would be if this were your factors, but if you took a 2 out of both of these terms, what would that second number turn into?
Oh, oops.
Yeah. You can't. So just factor that denominator, really. We take out a 2x, leave us with x minus 3. Anyone else get those 2 factors, a 2x and an x minus 3? Yeah. So then the vertical asymptotes would be at x equals what 2 numbers? Good. A 0, right? That's for this first factor. A lot of times students forget about that. 2 times what is 0? 0, Or a positive 3, right? Those are going to be our 2 vertical asymptotes. We okay with this so far? Again, is this an extremely difficult skill to do? No, it's not. You just have to practice enough of these so that you remember, okay, vertical asymptotes, that's what makes the denominator a 0, factor it, and then just like flip the signs, right? These are easy skills, but there's 5 different things to remember, 5 different properties of these graphs that you need to do. So you've got to practice them to make sure you understand them. But they are very simple calculations in themselves. All of them are. It's like I'm trying to encourage you to do your homework or something. That's weird. It's like it helps you learn things. All right, this is the weirdest part of the hyperbola. All right, you can have a hole in your graph, which seems really strange. So let me kind of talk about this concept first. There's some graphs that will just have a hole right along the line of the graph. And if you think about the way that these graphs are created, there's like an infinite number of points, aren't there? Like along the graph's line that actually makes it up. And so what happens is you got points at all these numbers, but then when you get close to a certain number, like in this case a 4, it skips over it, but then continues on right after it. It jumps over that hole. Meaning this graph is defined or has a y value for every x up to that hole and after that hole, but not right there at that spot on your graph. This is kind of similar to when we were graphing inequalities on a number line. Do you remember if we had something like, hey, that's a 0, and it's an open circle going to the right? Do you remember doing those open circles? Like that concept meant that anything bigger than 0 in this case is part of the solution, but 0 itself is not. But you can get really close to 0, right? Like you could do 0.00001, and it works as part of the solution, but you go over to 0 and nothing. It doesn't work. That's the same idea between a hole in the graph. It's two-dimensional, left, right, and up and down, instead of just left and right, one-dimensional like on that number line, okay? Now, why do these holes occur? Where do they come from? Well, take a look at this function right here. And first off, can we factor that at all? For sure. In that numerator, what could we factor out of both terms? 4. All right, so let's take a 4 out. Leaves us with x minus 4. How about that denominator? That's the difference of squares. So we'd write this as x plus 4 and x minus 4. Hey, does anything cancel out? It does. So right here at this step, when you have one of these functions, that you're going to graph, and you factor it out, and you see that something cancels out, That tells you right then and there that you will have a hole in the graph because something cancels out. And that hole is a point. It's an ordered pair, so we need an x and a y. Any guesses as to what the x coordinate will be for this hole?
0.
So it's just like the asymptotes we just did for vertical asymptotes, how you flip the sign. It's going to be for whatever canceled out. So we have x minus 4 and x minus 4 canceled out. And you flip the sign, and it's going to be a 4. Now, why, though? Well, take, for example, if x did equal 4, what would this entire numerator equal? Well, no, if we plugged in a 4 for x, what's 4 minus 4?
0.
It's a 0, and the whole thing would then be a 0, right? Anything times 0 is 0. What about the denominator? What would that equal? If I plugged in a 4 for x, you'd have 4 minus 4, which is 0, times 8, but isn't that still going to be a 0? And so the issue with holes is that they give you a situation where you can have a 0 divided by 0, and this is a little perplexing. Because for pretty much everything else in math, if you have some number and you divide it by itself, what does it always equal? 1, right? Anything divided by itself equals 1. That's been drilled into our brains. Even x divided by x, whatever x is, doesn't matter, it equals 1. So here you have 0 divided by 0. It's a number divided by itself. You'd think, hey, it's got to equal 1, right? That's a rule of mathematics. But there's another rule that kind of conflicts with this. Because I'm also dividing by 0. And what's the rule when we divide by 0? You can't divide by 0. So what is it? Is it a 1 or is it nothing? Is it you can't divide? Is there no solution? Oh, now you're just throwing out every term. So because this is a problem, like we don't really know exactly how it's defined, is we just say, you know what? Our graph is just going to skip over it. And that's what happens too. If you were to graph this on your graphing calculator or in Desmos or in Photomath, I don't know if you can graph in that, and you like traced your graph along every number, like for every x value, there'd be a y value. But when you get to 4 on this graph, it would say undefined. There's no solution. There's nothing that happens there. It's invisible. All right? You skip right over it, but then you keep on moving past it. So that's why we have holes in graphs. It's when something cancels out from the top and on the bottom. Like I said before, though, it is a point, an ordered pair, an x and a y. The x value we get just by flipping the sign of the factor that canceled out. How do you think we can get the y value of the hole? Just like any other, coordinate we're trying to find in math, if you have an x value, just plug it back into the equation to get the y value. The one thing you have to be careful of is don't plug it back in to the original problem, because then we'd get 0 over 0, which we want to avoid, right? That's why we canceled out those factors to avoid that situation. Instead, we're going to use the simplified one. After I canceled those out, the x minus 4s, we'd get this function here in red. That's the one that you want to plug the x coordinate of the hole into to get the y value. So just simply do 4 over, I'm going to plug in the 4 from the hole right there. And so 4 over 4 plus 4, that's 4 over 8, or simply 1/2. So 4, 1/2 is the location of the hole on our graph. Now, one nice thing about having a hole somewhere on your graph is it helps you determine where those two curves should be. So on the very first slide that I showed you a graph of, we saw curves in these two quadrants, right? The lower left and the upper right. However, if there's like a negative somewhere and it flips, like if it's reflected vertically or horizontally, these two curves would be in the opposite corners. And so we had to have at least one point to help us identify, well, which graph is it? Is it going to be these two or those two? And it always like switches diagonally. When you have one curve, it always jumps to the other side diagonally. But if you know that, oh, there's a hole in the graph right there, then you know it's got to be that situation where it's, oh, if it's in the upper right, I know it's also going to have a curve in the lower left. It always flip-flops between up and down. All right, can you identify the hole for this graph here in example 3?
You're gonna have like talk tonight? Yeah. What about like on
So there, yeah, it's due on Tuesday, and it's just we have 5 different like properties that we're calculating for these. So your delta, it's 5 sections, one for each of these different properties.
Okay.
Just one is just identify the horizontal asymptotes. The next one is identify the vertical asymptotes. That's all you have to do for each one of them.
Okay.
And
then
so,
on Tuesday, can I expect this to have on it too? Because I won't be here.
oh yeah. So then on Tuesday we're going to be putting it all together. So after you have those 5 different properties, then it's going to be put it on the coordinate plane,
Okay.
which is actually pretty simple, right? You're drawing 2 lines, plotting intercepts or the whole, and then just drawing in the curve.
Okay. Sounds good. Thank you.
You bet.
So is it just gonna be 4 and negative 6?
So look at what you canceled out.
Mm-hmm.
That's what tells you your x coordinate. Like what number for x would have made that a 0?
Okay.
But you have to flip the sign, right? Because it's going to be the opposite of that.
So then
And then plug this into that equation to get the y value.
either one?
Both. Plug it in for all the x's.
Is that it? Because then that would make it 0, and then
This isn't that factored. It's got to
Oh,
multiply
that'd
to
be
8 and add
16.
6.
oh. So I'd plug in 2.
Flip the sign.
Oh, so
Because you want to know what would make that into a 0.
and then I plug this in for.
Both those x's. That's right. All right, I'm seeing x plus 2, x plus 4 over x minus 6, x plus 2. Okay, first, everyone, did we factor correctly? After seeing that it was wrong? That's fine. Hey, does anything cancel out?
Yeah.
That's right. So as soon as something cancels, you know, hey, there's going to be a hole somewhere in the graph. And you need those coordinates, that x and the y coordinate of the hole for your graph. And you start by looking at what did you cancel out? And you just think, hey, what x value would make that factor into a 0? Well, if this says x plus 2, you know the hole is going to occur when x is a negative 2. Then to get the y value, just plug that negative 2 into the simplified function. And you're going to get a negative 2 plus 4 over negative 2 minus 6, which equals 2 over negative 8, simplifies to negative 1 over 4. Who's got that one right? Yes. Then you just plot that on your graph as an open circle. And then you know that when you do draw in the curve, it'll go towards that point, skip over it, and then continue on just past it. Okay, last 2. These are very simple concepts because we've seen intercepts on every graph we've ever graphed in all of algebra for all of our lives. And the rule is always the same for intercepts. To find an x-intercept, you make the y a 0. To find the y-intercept, you make the x a 0. Okay, you just always make the opposite variable a 0 and solve. So in this situation, to find the x-intercepts, you just make the y a 0. Remember, f of x is just a fancy way of writing y. So if I make this fraction equal to 0, well, there's still a lot of x's to solve for, but we can actually take a little bit of a shortcut here because it is a fraction. I've got a numerator and a denominator. Now, if we have a fraction, and I know that that fraction equals 0, which part of the fraction do we know actually has to equal the number 0? The numerator or the denominator? Ooh, which one is it? The numerator. Do we want the denominator to be a 0? No, but if the numerator is a 0, we'd have 0 divided by some number. And what do we know? 0 divided by anything is always going to equal. Always a 0. Whew. 0 divided by anything is 0. So all I really care about is what values for x would make the numerator a 0. Because if that numerator is a 0, the entire fraction will be a 0. Right? It doesn't matter what I've got on the bottom. And so we just need to look at the top. Now, as always, let's factor it just to make sure nothing cancels out, because there might be like a hole in the graph. And so real quick, we've got x minus 6 and x plus 1. On the bottom, we have x plus 3 and x plus 1. What do you think? Do we have a hole?
Yeah.
Yes, we do. So you take out the hole first, and now look at what we have left over. X minus 6 over x plus 3. And so to find an x-intercept, we really just want to know, hey, what value for x would make the numerator a 0? Yeah, just a 6. Because if this whole fraction equals a 0, I just care, well, how would x minus 6 equal 0? Because if that's a 0 up top, the whole fraction is going to be a 0. And so we know that there's an x-intercept whenever x equals 6. And so you'd say, all right, so there's an x-intercept at the coordinate 6, 0. So write it as an ordered pair. That's how Delta Math is going to want you to do it on your homework this weekend. And so that x-intercept, that 6, that's your x-coordinate. And then the y-coordinate is always going to be a 0. For the y-intercept, we just do the opposite. Right? To find the y-intercept, you make the x a 0. Now this is actually pretty simple, because if I were to make all the x's a 0, what happens to them? Like this term, 2 times x, if that were a 0, what happens to the 2x? It's gone, right? You can just cross it out. And this is true for everything with an x in it. You basically just ignore, because even down here, if x were a 0, 0 squared is 0. You don't even need to worry about it. So basically, just cross off everything with an x in it. And now look what we have left over. A negative 4 over negative 4. What does that actually equal? Just a positive 1. So then our y-intercept will occur at the coordinate 0, 1. 0 is the x-coordinate, right, for every y-intercept. So that's how I know that's a 0. But then the y-coordinate is going to be a 1. Isn't that easy to do? Oh my gosh. To cross off everything with an x, that's tough. Oh my goodness. Perhaps. Depends on where you're coming in. All right, so I've got one more to find the x and the y-intercepts. So let's start by factoring it all out. We love factoring. We're going to be champion factorers. By the way, down on the bottom, there's a negative in front of the x squared. That's a little dangerous. We don't like that. So I'm going to take that negative outside and make this a positive x squared minus 2x minus 3. Now I can factor that denominator nicely. X minus 3, x plus 2. I'm sorry, x plus 1 I meant. Does anything cancel out? Those x plus 1s. So we're left with x plus 3 over negative x minus 3. You can distribute the negative or just leave it there. Okay, so we simplified it. Now, x-intercepts, what would make the numerator a 0? Yeah, you just flip the sign. That says x plus 3. So if x were a negative 3, so our x-intercept is when x is a negative 3, and our y-intercept, well, I know that there's going to be an x-coordinate of 0. What's the y-coordinate? How do we figure that out? Do you remember what we do? Yeah, just take away all the x's. And you can do it in the simplified problem, or you can do this in the original one. And just look right there. What's 3 divided by 3? It's 1. So we have a y-intercept at 1. So I hope you realize that these are pretty simple calculations that we're doing here. It's just there's 5 different things. And so you got to keep straight, hey, which simple calculation do I use for the asymptote versus the intercept versus the holes? And that's what you're going to practice over the weekend. Your Delta Math has 5 sections, 1 for each of those properties, okay? And so you're going to practice each of those in isolation. And then next class, we'll put it together for the graph.